Okay, so we're just finishing up example 3 for today. We're looking at a vector field for with 3 variables, x, y, and z. And we're trying to find that potential function f, a function of 3 variables, x, y, and z. So just a little bit more detailed in terms of that process, but a very similar thought process. We start with the fact that if this is my gradient, then each of these represents the partial with respect to x, partial with respect to y, and partial with respect to z. So I started with my partial with respect to x, and I integrated it with respect to x. I had to account for the possibility that there was a part of my initial function that only involved y and z, and so when I differentiate it with respect to x, I lost that piece because it was just a constant. Okay. So now what am I going to do with that? Same thing we did in example 1. I'm going to take the derivative with respect to y. I'm going to take my y partial of this. So if I take my derivative with respect to y here, what am I going to get? I'm going to get 2xy. This is a function of 2 variables. So I'm going to get, watch, g sub y of this function yz, whatever that partial is. And I'm going to think about how that compares, right, to my actual partial for y. That tells me that g sub y, right, that partial must be e to the 3z. I'm going to take that partial and I'm going to integrate. So this is almost now going to look exactly like example 1 because I have a function with 2 variables and I'm trying to go to 1. So we've essentially eliminated a variable at this point almost. So I'm trying to, integrate with respect to y, right? Integrate with respect to y. And I'll be able to try to figure out what that function g of yz is. If I integrate with respect to y, this is just going to serve as like a constant, right? A coefficient for y. So I have y e to the 3z, but what about the chance that there was some part of my function g, that's a function of just y and z. There's a chance that there was a part there that just involves z, and when I took my partial with respect to y, I lost that. So I'm including that part back. Okay? So maybe hit the pause button, make sure you kind of understand that flow so far. Okay, I'm going to go back to this step up here where I have my function f. And I'm going to replace g of yz with this. So I have, I'm going to use a new color, I have this f of xyz is going to be xy squared plus, and instead of g of yz, I'm now going to write what I just found g of yz to be. Still sort of has that unknown factor in it, right? So how can I help to eliminate that? This is what we're going to do. We're going to differentiate with respect to z. We're going to find that z partial. My z partial, right? So I'm taking the derivative of this, partial derivative with respect to z. This part just disappears. Right? This part here, I'm taking that 3 out of my exponent, ye to the 3z, right? Y is just some coefficient, plus h prime of z. I'm not sure if you can see this is a z, so I'm just going to make that a little clearer for you. Taking the partial with respect to z. Well, how does that compare to my actual partial with respect to z? Looks like h prime of z is just 0. My actual z partial is just this piece here. So what does that tell me? H prime of z must just be 0. So now I can go back to this line. X, y squared plus ye to the 3z. If my h prime of z is 0, what's h of z? Just some constant, so it's just my plus k. And that would be my function f, for which this vector field would be the gradient vector.